Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is the Milliken Experiment, and I think you're going to enjoy this one. This is an experiment carried out by a physicist by the name of Robert Millikan in the 1800s, if I remember correctly, which is not to say that I was alive in the 1800s, but that's what I read. And what he was measuring was, or attempting to measure, was electrical charges. And the way he went about this was he reasoned that in nature there must be, we knew there, of course, at that time that there were particles that contained electric charge, but he figured there's got to be some particle that carries the most basic or the smallest unit of electric charge. Of course, today we know that that is the electron as one example. Protons also carry the same magnitude of charge, just opposite sign as the electron. But back then, it wasn't entirely clear how did objects pick up charge. And his idea was that, well, they pick it up by gaining or losing electrons, and therefore each electron which carries the negative 1.6 by 10 to the negative 19 coulombs that we've studied so far in this course, that would be the sort of basic unit, as it were. So he set up this really ingenious experiment to measure this electric charge, and I had the pleasure of actually doing this experiment when I studied physics in third year. So it's a fun experiment, and it was really neat to actually do this and measure something so fundamental to nature. And today it's my honor to explain it to you. So here are some of the questions that we're going to be addressing about the experiment. And also here's where we are in the unit schedule. Here are your learning goals and success criteria. Take a moment to view those, pause the video. When you come back, we will go over all the details of the experiment. Okay, and you're back, and let's get started. I'd like you to start off by looking at this set of images, which is from the Wikipedia page on the Milliken Experiment. Here's the basic idea. There is an oil sprayer, or a spray can connected to some oil, and what it does is it sprays oil through a very fine nozzle called an atomizer. And that doesn't mean it breaks the oil into atoms, it just means it breaks it into a really fine mist. Think of the spray coming out of a cologne or a perfume bottle. Anyway, the oil droplets go through this covered area, and they fall through this tiny little hole here into a set of oppositely charged parallel plates. Now you know why we were studying parallel plates. At least one of the reasons is they are central to Millikan's apparatus here. Now, the parallel plates are connected to a power supply which provides the delta V, the electric potential difference between the top plate and the bottom plate. So I'll add in delta V, which we studied in the last video. Now, there is a microscope which is pointed in between the parallel plates, and you can actually see the oil droplets enter around here into the parallel plates and watch their motion. Now here's a device which maybe he used, or maybe it's an earlier or a later device, a little more modern, although it looks kind of old. You can see the oil, the source of the oil, and here of course is the microscope. Back here would be a light, kind of like a microscope that you're used to seeing. It has a light to illuminate the specimen, and in here, this tiny little part here that I'm circling, that's the parallel plates, and it's got to be connected to a power supply. Now let's look at a schematic diagram to show in a little bit more physics detail what's going on. This image is from your textbook, Physics 12 by Nelson, and you can see the parallel plates are connected via a power supply. This one has a symbol that maybe you don't recognize, the diagonal line through the series of cells here. This tells us that it is a variable power supply, which means you can adjust the voltage. So we'll call it delta V, as we've been calling it already, but keep in mind you can change this. So anyway, the oil droplets, they can either fall in through the top, you can cut a little hole in the upper plate, or as I did it when I did it in third year physics, we sprayed the oil droplets in the side. It doesn't really matter as long as the droplets get in there. Of course, the microscope here has been omitted because it's not really important to the physics of what's going on here. Anyhow, each droplet, of course, has a certain mass, and here's something interesting. It's got a charge on it. Now, why would the oil droplet have a charge? Well, you first might answer that, well, the oil droplet is composed of atoms, which is true. Each atom has protons and electrons in it, that is true, and therefore there are charges. But remember, matter normally is neutral. That is, most matter, desks, floors, doorknobs, radios, cars, whatever you happen to touch, your food, you don't get a shock every time you touch them. It's because the electrons and protons balance. It's only when things get charged that we have a net charge which can be influenced by an electric field. Why are these oil droplets charged? The answer is that when you spray them through this sprayer here, this atomizer as it's called, so I'll write that in, what ends up happening is the droplets pass through the really tiny nozzle and they encounter some friction. And so you end up with having some of the droplets charged by friction, the same process that causes your clothes to come out of the dryer with a sort of staticky, or a static cling, I think they call it in the TV commercial, where they tell you to use fabric softeners. Same thing's going on here. Now, there's just one problem. We don't know how many charges each oil droplet has. Some of the oil droplets may have gained or lost one electron. Of course, if they've gained or lost one electron, then they either have plus or minus 1.6 times 10 to the negative 19 coulombs. If they gained an electron, it's the negative charge they have. If they lost an electron, then positive. If they gained 2 electrons or lost 2 electrons, now we're dealing with 2 times this number, which would be 3.2 times 10 to the negative 19 coulombs. 3 electrons gained or lost, plus or minus 4.8 by 10 to the negative 19 coulombs, and so on. I don't know what is the maximum number of electrons that can be gained or lost, or what is the average. That's not really important at the moment. The important thing is to realize that these objects, these oil droplets, can be charged, and they have mass. So now let's think for a moment. Because they have mass, they will have the force of gravity acting on them, and that is shown in this diagram by Fg as a downward vector. I'll just highlight that in green so that you remember. Of course, we know that Fg is equal to mg. That hasn't changed. On the other hand, because these objects are charged, they will experience an electric force, which is shown by this vector. Now, in this particular diagram, they've shown the upper plate negative. You can see it's attached to the shorter terminal here, which means negative. The longer one means positive. This is positive, that's negative. Keep that in mind. Now, if this is negative and they are showing the electric force directed upward, then that means that these objects, these oil droplets, must be charged positive. Otherwise, they would not be attracted to the upper plate. Another way of looking at it is that they are repelled from the bottom plate. So, based on the diagram and the power supply, we know that the charge must be positive. What is the force that is acting on them? The electric force, well, to think about this one, I guess you have 2 choices. You've all seen this formula, Fe equals K big Q little q over r squared. Is this the formula that we should use? Well, if you think back to the video where we talked about parallel plates for the first time, remember, in a parallel plate apparatus, there are many, many, many charges on the top plate and many, many, many charges on the bottom plate. That's what it means to have these oppositely charged parallel plates. If you want to figure out the force on this oil droplet by thinking in terms of this formula here, you're going to be here until, well, probably the rest of your life, because there are so many charges on the upper plate and so many charges on the bottom plate, and there are potentially many charges on the oil droplet, you would have to calculate all the imaginable combinations. So, do we want to use the formula for the electric charge between 2-point charges when there are so many charges? No, don't use this formula here. Use another formula. What other formula can be used? Well, if you recall, we also know that if the electric field is given, then here's a formula that can be used. F equals Q, the charge, times the electric field. It's kind of analogous to Fg equals mass times the gravitational field. We discussed this formula way back when we started looking at electric force and electric field. Well, this is a much better formula to use than this one, because if you know the electric field due to parallel plates, and you do know this one, E parallel, I've been writing it as E with two parallel lines. If you remember that, it's very simply the potential difference between the plates, delta V, divided by the distance between them. Here they use the letter R, and I'm afraid if I use the letter R, you're going to think of this letter R. So, sorry textbook, I hope you don't mind. I'm going to cross that out and put the letter D in there, and put the letter D in here. That way you won't get confused. All right? So, anyhow, getting back to what's going on here, the oil droplet has been charged by friction. It's entered the parallel plate apparatus. It's experiencing, if we set up the polarity of the power supply correctly, it is experiencing an upward electrical force and a downward gravitational force. What did Millikan do? Simple. He altered the variable power supply. He turned the dial until the electric force up exactly balanced the gravitational force down. Because once that happens, he's able to write this. Fg equals Fe. Mg equals Qe. Or Mg equals Q, sorry, not E there, but delta V over the plate separation. Now, as you can imagine, an oil droplet does not have a lot of mass. This is going to be a really small number here, and for that matter, how do we measure the mass of an oil droplet? G is 9.8. Q is what's unknown, and that's the thing he's looking for. So what I'm going to do right now is just isolate Q. What do we get? Mg times D. D is the plate separation, which, as I'm sure you can imagine, measuring the separation of the two plates here is not hard. The manufacturer would probably tell you what the plate separation is, or if you were a physicist, you'd probably build it yourself, and you would know. And then, of course, we divide by delta V, and delta V is just the potential on the variable power supply, and that can be read with a simple voltmeter. So let's go ahead and categorize each of these variables as either easy to find or hard to find. Let's go. Delta V and D, these ones are easy. It's really just a matter of making a measurement with pretty much a ruler or making a measurement with a voltmeter. What other variables here do we need to look at? We got to look at the mass, and we need to look at G. G, of course, is 9.8. We don't have to measure that anymore, so let's just categorize it as easy. I guess the tricky part here is going to be the mass. If we want to know the charge on the droplet, we have to know the mass. But how the heck do you measure the mass of an oil droplet? You might say, well, just grab the oil droplet that you're looking at, take it out of the apparatus, and stick it on a scale. But come on, how could you possibly pluck an oil droplet out of the air and place it on a scale? It would be so hard to do that this is not a very good strategy. So here's where I've got to take you all the way back to the very first chapter that we did in this textbook, where we started learning about the concept of terminal speed. Let me show you what I mean. I didn't prepare a slide here, so give me a moment. Let's call this Measuring Droplet Mass with Terminal Speed Ideas. Here's what I'm talking about. This is what Millikan did. He looked through the microscope, right here, at the oil droplets, and he adjusted the potential difference until one of the oil droplets, sort of his target oil droplet, was hanging motionless in between the parallel plates. That's when he knew that the forces were balanced and he could use this equation. Then what he does is something very clever. He turns off the electric potential, and as a result, there is now the following force acting on the droplet. Just gravity. Because he has turned off delta V, turn off the power supply, delta V equals 0, therefore we have Fe equals 0. No more Fe pointing up. the oil droplet begins to accelerate downward. However, think back to what we learned about really light objects, such as an oil droplet, falling through the air. Do you remember what it is? They very quickly encounter a lot of drag, Fd, and as a result, this leads to terminal speed. So suddenly drag becomes significant, and when these two are equal, we're at terminal speed. Now, what do you remember from our discussion of terminal speed way back at the beginning of the course? The idea was this: heavier objects have higher terminal speeds. Heavier object leads to greater V terminal. So, heavy, that is mass. Terminal speed, how do you measure this? If you could just measure terminal speed, you'd have an idea of the mass, which would solve our problem here of not knowing what to put in here. Well, how does he do it? When he turns off the power supply, and the electric field becomes zero, and the electric force becomes zero, the droplet begins falling. I know the forces are balanced here, but that just means that acceleration equals zero. It doesn't necessarily mean that v is equal to zero. Remember, acceleration can be zero, forces can be balanced. You can be moving downward at a constant speed. So what does he do? Well, inside the parallel plate apparatus, and possibly built into the microscope here, is a simple ruler. If you've ever studied in biology class, if you've ever studied cells under the microscope, I know when you're learning how to use a microscope, they sometimes want you to calculate the field of view. So inside the microscope, maybe on a slide, is a ruler. The ruler looks something like this. It's got little tick marks every millimeter or whatever the case may be. Since the oil droplet is falling at a constant pace, we can simply say that the V terminal equals a certain distance divided by a certain time. It's actually an easy thing to measure. Once we know the terminal speed, we relate that back to the mass. Now, how do we relate terminal speed to mass? This is a branch of physics called fluid dynamics, where you have to ask yourself, how does the density of the air and the speed of the falling oil droplet and the viscosity of the air and so on and so forth affect the drag force? Well, there is a formula. It's a kind of a messy formula, but it is interesting to look at. You might wish to look this up after this video. However, let's just leave it, let's suffice it to say that the greater the terminal speed, the heavier the mass. It's done in this way. And now we know how to get this number in here. So in the end, Millikan is able to measure the charge on any given oil droplet. But he doesn't know, is that charge due to one extra or deficit electron? Is it due to plus or minus, so a deficit or extra 2 electrons, 3, maybe a huge number like 100? Who knows? How does he figure it out? Well, the idea is this. It's to repeat this experiment many, many, many times and look at all the charges you get for various different oil droplets. And painstakingly, in the 1800s, without the use of computers, look over all of these charges and see if you can figure out, it seems to me that each of these charges is due to some basic unit or basic multiple. What did he find? He found that the basic multiple was this number. 1.6, or let me try to draw that correctly there. He found that the basic unit, the basic multiple, was 1.6 times 10 to the negative 19 coulombs. And you will, of course, recognize this number. This is the charge on an electron. And so Millikan took that to be the charge on an electron, which he estimated was, or proposed as what was causing the charging. And this is known as the elementary charge. Elementary as in basic, no smaller unit. Elementary charge. Of course, protons carry the same charge, just positive, but protons don't do the charging. They're stuck deep within the nucleus, right? Let's do one calculation and then we'll finish up here. This is sample problem 2 from section 7.5 in the Physics 12 book by Nelson. In a Millikan type experiment, two horizontal plates are 2.5 millimeters apart, so I'm going to start off drawing that right away. 2.5 millimeters is what the distance is equal to, okay? And this time not an oil droplet, but a latex sphere of mass 1.5 times 10 to the negative 15, that's a really tiny mass, by the way, remains stationary when the potential difference is 460 volts with the upper plate positive. So how do I draw this? Long line means positive, short line means negative. So we've got this variable power supply, and we've decided that one of the spheres can become suspended in midair at 460 volts. Okay? Upper plate, of course, positive. Negative on the bottom. So here is the droplet. We can draw in some of the forces. We know that gravity would always be acting down. The electric force would always be acting up, and these two are equal. So we can start saying something like this. Fe equals Fg. Qe equals mg. Q delta V over distance, which is the formula only for parallel plates, is equal to mg. And so now, question A. Is the sphere charged negatively or positively? Well, I see it's being repelled from the bottom, attracted to the upper plate. Attraction to positive, repulsion from bottom must be negatively charged, the oil droplet, which is going to mean there are excess electrons on it. When it was charged by friction, it gained electrons. Okay? Calculate the magnitude of the charge, no problem. That's going to be Q, which is mg times d over delta V. I can plug in these numbers, 1.5 times 10 to the negative 15. G is 9.8. Need a little bit more space here. Oops. Distance, make sure you convert to meters here. And divide by, that should be delta V 460. Let me just run this calculation really quickly. I'm not going to bother pausing the video. 1.5 times 10 to the negative 15 times 9.8 times 2.5 by 10 to the negative 3 divided by 460 equals, and I get a pretty small number. In fact, so small that I'm going to check again. I know what I did wrong. Let me actually show you the mistake that I made, and then I'll tell you how I knew there was a mistake right away. 1.5 times 10 to the negative 15 times 9.8 times 2.5 by 10 to the negative 3 divided by 460. Okay, here's what I did the first time, and I calculated this. 7.989, that wasn't the problem. In fact, I didn't punch in anything incorrectly. Q charge is measured in coulombs. Okay, now what did I do at this point? The next thing to do is to say this is the total charge, and to realize that this is due to some multiple of electrons. So the next step that Millikan did is he asks himself how many electrons are responsible for this charge. Because if you think about it, charging by friction, you can add or take away 1 electron, or 2 electrons, or 3, and so on. So here's what he does. He says that the charge, Q, is equal to some number, n, times E, where E is equal to our good friend 1.6 by 10 to the negative 19. Okay? And n, of course, is equal to 1 in the case of 1 electron, 2, 3, and so on. It's an integer, positive integer. Now, what would have happened here if I had done this? I would punch in 7.989 times 10 to the negative 20 is equal to n times 1.6 by 10 to the negative 19. And I'm going to need more space here just to finish off. What would I get if I did this calculation? 1.6 by 10 to the negative 19, and I get this number. N equals 0.499, or 0.5. Does this number strike you as odd? I hope it does. It's telling you that there is half of an electron charging up this latex sphere, which is impossible because electrons are elementary, basic particles. They can't be divided down any smaller than themselves. It would kind of be like saying I've got half of a penny in my pocket. You can't have that. Now, when I ran this number over here, I immediately noticed that the total charge on the droplet was less than the charge on one electron, so right away I knew something was wrong, and I almost corrected myself, but I thought, you know what, I'll show you how you sometimes go through a problem without catching a mistake until you get to the end, and now you know something's wrong. Did any of you detect where I made the mistake? The answer was actually right back at the very beginning. This was 2.5 centimeters. I wrote it as millimeters, which caused me to put 10 to the negative 3 here. I should have put 10 to the negative 2. That would have made this 1 order of magnitude higher at 10 to the negative 19, which would have made its way through here, which would make this number 10 times higher, 5. All right, so you got to see a number of things there, some on-the-spot problem solving, as well as the Milliken experiment. I hope you enjoyed. That's it for this video. Thanks for watching, and I'll see you in class.